Hi, my name is Gary Millette. This is ELE-111, Internet of Things, Fall of 2021 semester. This is topic number 5, Electrical Quantities in Units and Fundamental Concepts. So let's get started. Over the course of time, the various scientists around the world have agreed on fundamental units of measurement. So here we see some physical, electrical, and magnetic units of measurement in this chart. They're called the International System of Units, or SI for short, and there are fundamental and derived units. So the fundamental units are length, which is a meter, with a symbol of small m, mass, kilogram, with a symbol of small kg, time in seconds with a symbol of a small s. Electrical current is a fundamental unit, and it's ampere and capital A. Temperature, fundamental unit, Kelvin, capital K. We don't use that very often. Luminous intensity, candela, small cd. The amount of a substance is a mole, small mol. So these are all fundamental units. Here you see a picture of a meter stick and a yardstick on a table. Also a foot-long ruler and a tape measure. So length, we have meters, and the basic unit of length is, in the rest of the world, the meter. And of course the meter stick's about 39 inches long, a little bit longer. A yardstick is 36 inches long, that's the shorter one there shown. And a ruler, the purple one, is 1 foot or 12 inches, and of course there's a tape measure. The fundamental unit of mass is the kilogram, or kg. This shows a scale with a kilogram on it, and a kilogram is basically equal to 2.2 pounds. And of course, the MKS system, the only thing we tend to use in the United States is the second. Mass, again, length and so forth, meters and kilograms tend to be used in the rest of the world, not so much in the United States. So again, the kilogram is the fundamental unit of mass. 1 kilogram is equal to approximately 2.2 pounds. And as you can deduce, drug dealing, which is international activity, uses the kilogram as a unit of measure. Now, it turns out that we like to take and say we have standards for these units, and this picture shows the standard kilogram as it is stored. Notice it is within 2 bell jars. So the kilogram is this platinum piece of metal in the smaller bell jar, which is contained in a larger bell jar. And again, it turns out we go to great lengths to keep these standards. Of course, for time, we use second. Here's a clock face, an analog clock face, if you will. So the agreed upon unit of time is a second. A time standard is created by an atomic clock. Time is a elusive unit since it appears to change as one ages. I have to change that slide. Sense should be S-I-N-C-E. So we have some time standards. We have atomic clocks and network synchronization. So atomic clocks are used to define the International Atomic Time. There's a stratum 1 frequency reference in telecom networks for synchronization. We use atomic clocks for global positioning systems, or GPS. You see the little diagram there shows the Earth showing a bunch of satellite, constellation satellites for GPS. And we use scientific clocks also. So network synchronization is extremely important for telecom, the power grid, electronic financial transactions, and so forth. So you see 4 little pictures there of a network on the far left, a picture of the world, Wall Street, and power grid. So it turns out, again, especially as we go into the Internet of Things, there'll be a need for low latency and very accurate time. We have developed time-sensitive networking, or TSN. So as we find out here today, due to computer networking applications, we need to build time-sensitive networks. So this shows a time, excuse me, a time-sensitive networking switch with a switching fabric and 3 data streams coming in. And notice that depending on the importance of the message, one may get priority over the other 2. Switching gears a little bit, let's take a look at the ampere, which is a basic unit of electric current. So here we see a wire, and we see these little Q's, which are electrons or charge. So electric current is defined as a rate of flow of electrons. 1 amp is equal to 1 coulomb per second passing a given point. That point is that area, this round area labeled A in the diagram. Today we have some interesting tools at our disposal, things like infrared cameras and so forth. So the basic unit of temperature is the Kelvin. However, we hardly ever use that. Instead, we use Celsius, which is abbreviated C, and Fahrenheit. Here in the United States, we tend to use Fahrenheit more than we do Celsius. This is kind of interesting today. A smartphone app shows a infrared camera attached to it, and this shows a picture. It looks like a sink, where apparently the sink is running hot water through the spigot. And again, this is something that you can connect to a smartphone. As far as luminous intensity, the candela is used. So this shows a light source, and it shows a half of a hemisphere, semisphere, I guess you call it. And it's a fairly obscure unit, the candela, but it shows that on the surface, some distance d from that light source, we get 1 square meter, and we would take and use that as the intensity of the light source at some distance d. Mole, or the amount of substance, well, chemists use the mole as a measure of the number of particles of a substance. So the definition really is 6.022 times 10 to the 23rd particles. They could be atoms, molecules, ions, formula units of a substance. And we show, in that case here, the diagram looks like water or molecules on the left-hand side, atoms for copper in the middle, and formula unit on the right-hand side for some type of compound or substance. Continuing with electrical magnetic units of measurement, we have derived units. So for a quantity and a unit and a symbol, for angle being the quantity, we have a unit of radian, a symbol small r. A solid angle, refer back to the slide before about the candela, we have a steradian, or SR, small sr. So radians are used when doing calculations involving sine waves, and steradians are typically used when doing calculations involving antenna patterns and laser beam intensity. This shows more about a radian. Radian is defined as the angle which subtends the radius of a circle on its circumference, and it turns out that there are 2 pi radians in a circle. So 360 degrees is equal to 2 pi radians. Here's the steradian, and notice it's a solid or 3D measurement. The steradian adds an additional dimension to the radian, making a 3D measurement. And again, you could understand how that might be for an antenna located at the center of that sphere, or maybe a laser beam, or a flashlight, if you will. Now, changing our attention to units of energy, we have the SI units for energy. The SI unit of energy is a joule. A joule is defined as 1 kilogram times meter squared per second squared, which equals actually 1 Newton times a meter. Newton's a unit of force. So shows mass times velocity squared, mass times gravity, the acceleration of gravity times the height of the object. On Earth, g is 9.81 meters per second squared. There's a few more minutia things here. For an ideal gas, we have C sub V, K sub Bt, where C sub V equals 3/2 for a monoatomic gas. Power is energy per time. 1 watt is equal to 1 joule per second. Most commonly used in electricity, but also for vehicles and horsepower, acceleration time. So, returning to some more common units here, electrical quantities, symbols, and derived SI units. So, most electrical units are derived from more fundamental units. So, in this chart, we see capacitance with the symbol C. The SI unit is a farad, and the symbol is capital F. Charge, symbol capital Q. The SI unit is coulomb, symbol capital C. Conductance is capital G. SI unit is Siemens, capital S for the symbol. Energy, again, the symbol is capital W. The SI unit is joule. The symbol is capital J. Frequency. For sine waves, for instance, a lowercase f. SI unit is hertz. Symbol is capital H, small z. Impedance. These are things which we talk about in circuitry. The symbol is capital Z. The SI unit is ohm. And the symbol is an omega, Greek omega. Inductance for a coil is L. The SI unit is Henry. And the symbol is capital H. Power. The symbol is capital P. The SI unit is watt. And the symbol is capital W. Reactance is capital X. SI unit is ohm. Symbol is omega again. Resistance is R, capital R. Ohms and omega symbol again. And voltage is capital V, or volt, and capital V. So voltage and resistance, probably things you've heard about before, is maybe power also with watts. Things like capacitance and inductance probably aren't as familiar to you. Frequency is another one you may have heard of before. So here's a picture to show all kinds of different capacitors. And what are capacitors? Capacitors store energy in electric fields that exist between two metal conductors that form the capacitor. About the only place you see that is in the diagram of the variable capacitors on the right-hand side of this diagram. Everything else is hermetically sealed, but you might guess that what happens is we take foil and separate it by an insulator and wrap the foil around itself so it forms the various capacitors. If you're interested, take a look on Wikipedia to show you how to make these things. The electric field takes time to be created, and thus the capacitors had to charge and discharge as a voltage is applied or removed from the capacitor. It does that in an exponential fashion. Here's a picture of inductors. Inductors appear to be coils of wire, and that's indeed exactly what they are. Inductors store energy in the magnetic field that builds up around the coil windings. Like a capacitor, it takes time to either energize the magnetic field or collapse it. Thus, the current through an inductor cannot change instantaneously. The inductor, like the capacitor, has a time constant associated with its operation. Today, a lot of inductors are wound as toroids. Resistors. So here's a picture that shows a bunch of different resistors. What do resistors do? They oppose the flow of current. The bigger the resistor value, the less the current flow. Resistors can be used to create new voltages in a series circuit or to limit the amount of current through a component like an LED, so it might not burn out if we allowed unlimited current to flow through it. So you see things like carbon and metal film in the top left-hand corner. They have color codes on them. You see thick film resistors below them and thin film resistors below them in the bottom left-hand corner. Wire-wound resistors for higher power in the middle. Special purpose resistors down below those. And adjustable resistors on the far right-hand side, where we can adjust the resistor value. Sometimes we call those rheostats, and you may have come across equipment, electronic equipment, that would have potentiometers as volume controls. Magnetic quantities, symbols, and derived SI units. You have another chart here. These are really kind of abstract things because you hardly ever hear of these. So let's just take a look at that. Magnetic field intensity, capital H. SI unit is ampere turns per meter. Magnetic flux has a symbol phi there, or it looks like a Greek symbol called Weber's. Magnetic flux density is B, or Tesla, capital T. Magnetomotive force is capital F sub M, ampere turn. Permeability is mu, another Greek term. Reluctance is looks like a script R. So again, these are kind of units you don't come across very often. They're not as commonly recognized as the electrical ones, but nevertheless, they are what we use today. So if we have a magnet, here's a picture of a bunch of different magnets. The bar magnet in the top left shows the South and the North Pole. All magnets have two poles, and notice the magnetic flux that emanates from the South and the North Pole. Magnetic flux is always closed, that is, forms loops. A horseshoe magnet in the middle upper part of that picture. An electromagnetic field is created with a coil or an inductor and a battery. As the current flows through the coil of wire, it creates a magnetic field. Down below, you notice unlike poles attract. The North and the South attract one another. Unlike poles, that should say, unlike poles repel, and then like poles attract over in the, which is, let me start again. It should say unlike poles attract on the bottom left, which it does. There's a North and a South pole. And then on the right-hand side, it shows two North poles. It should say like poles repel. Now, because of the way things have been invented or discovered, it turns out that things like the farad is a unit which is not really realized in normal practice. We tend to have things like 10 to the minus 12 farads or a picofarad. So we use scientific notation a lot of times when we talk about the units in electrical circuits. So powers of 10 are a form of shorthand notation. So you should be familiar with this, I would think, from someplace in your prior experience. 10 to the 6th is a million, so the exponent, the 6 there, tells you the number of zeros. 10 to the 5th is 100,000, or 5 zeros. 10 to the 4th is 10,000. 10 to the 3rd is 1,000. 10 squared is 100. 10 to the 1 is just 10. What about 10 to the 0? Anything raised to the 0 power is equal to 1. You may say, why is that? It's to make the mathematics work. Over on the right-hand side, we have negative powers of 10. 10 to the minus 6. You notice that the decimal point is 6 places to the left of the 1. 10 to the minus 5th, 5 places. 10 to the minus 4th, 4 places. 10 to the minus 3rd, 3 places. 10 to the minus 2, 2 places. And finally, 10 to the minus 1, 1 place. So we use powers of 10 as a shorthand notation for large and small numbers. So here's some examples of the use of scientific notation. So if you haven't done any of these recently, maybe you want to review this. If this is stuff that you know, you can skip over this. Here's another example. Again, if you are comfortable with this, you can skip over. If not, you want to take a look at the examples, just to make sure you know what's going on. Now, we also like engineering notation and metric prefixes. So engineering notation is limited to powers of 10 that are multiples of 3. So here's some examples. 82,000. Well, in engineering notation, 82,000 is expressed as 82 times 10 to the 3rd. 243,000 expressed as 243 times 10 to the 3rd. 1,956,000 is expressed as 1.956 times 10 to the 6th. We only use powers of 10, which are multiples of 3. So here's another example, engineering notation. So this use of powers of 10 that are multiples of 3 give rise to metric prefixes, which is more shorthand. So here's a table of the metric prefixes. This is as of today in 2021. When I was a young person, it turned out that a lot of these didn't exist. They certainly weren't in the modern vocabulary. If you're a computer buff, some of these, like giga and tera, have become popularized by personal computers. But scientists have come up with, again, these prefixes. So let's start with 1 in the center. And we don't tend to use this. A factor of 10 is a deca. A factor of 100 is a hecto. We use 1,000 as a kilo. 1 million is a mega. G is a giga. T is a tera. P is a peta. So when we get to giga, it's 10 to the 9th. Tera is 10 to the 12th. Peta is 10 to the 15th. Hexa, or capital E, is 10 to the 18th. Zeta, or capital Z, is 10 to the 21st. And Yoda, or capital Y, is 10 to the 24th. So it turns out that we have a lot of abbreviations for things that are bigger than 1. Notice as soon as you get to mega, they're capitalized. Below that, they are not capitalized. When you go the opposite way, a tenth is a deci, centimeter or centi, milli or m or 1,000ths, micro is mu or 1 millionth, nano is 10 to the minus 9th, pico is 10 to the minus 12th, femto, small f, 10 to the minus 15th, atto, 10 to the minus 18th, zepto, small z, 10 to the minus 21st, and a yocto, or small y, 10 to the minus 24th. As we have improved our instrumentation, we have kind of invented new symbols for things that represent either extremely small or extremely large numbers. And you notice these are all, again, engineering notation where everything is a factor of 3. So here's some examples of metric unit conversion. You should go over these if you're not that familiar with them. Otherwise, you can skip this. Here's some more examples. And a final example. So just to review, as you've seen, many electrical and magnetic quantities, symbols, and units. So the thing you should concern yourself the most about is shorthand notations. We like to use scientific notation because we have such a range of units. Engineering notation uses everything that are powers of 10 that are multiples of 3, which is the next term here, metric prefixes. New ones become common terms as technology marches on and our ability to measure things both large and small improves. So that's it for this presentation.